Okay.
All right. So, hello everyone. This is Chem E Car at IIT, and I am Alejandro Torres, the current Chem E Car coordinator and a first-year chemical engineering student.
Hey everyone, my name's Tom Doyle. I'm a third-year chemical engineering student, and I've also been involved in Chem E Car for a while now. So, yeah.
All right. So, what exactly is Chem E Car? Well, it's an annual competition and subset organization held by AIChE, the American Institute of Chemical Engineers, and the goal is to build a car that is autonomously operated and controlled by chemical reactions, which will not only provide the source of power and propulsion mechanism, but will also cause the car to stop at a specified distance between 15 and 30 meters while carrying a specified mass between 0 and 500 grams. Two competitions are held each year. There's a regional competition in the spring and a national competition in the fall. And these competitions are held worldwide, and the first of these was held in 1999. So what are some of the rules and logistics of this competition? How exactly does it work? Well, there are two main components of it. There's the evaluation section and the performance section. And so for the evaluation section, each car needs to you need to demonstrate that your car beforehand is safe enough to operate, so that they all know that you're not going to set fire to the building when it gets on the line. So because of that, you need to explain each different component of the car that even has the slightest potential to cause a hazard in lots of detail. It's a pretty tedious process, but it is necessary. And then for the actual, and then when you actually get to the competition, you have a while to prepare to get your car running and stuff. But then an hour before you had to start your car, they announced a distance between 15 and 30 meters. So you want to try to get your car to stop as close to the specified distance as possible. And they're also going to announce a random mass between 0 and 500 grams that they're going to add onto your car that you need to take into consideration going into a competition. And then once you get to the start line, you can only interact with the car up until it starts moving. And once it starts moving, you can't do anything to it because it's supposed to be autonomously operated. And then the performance section is judged based off of absolute distance between the car and the finish line. And then the team with the car that finishes closest to the finish line wins. And here's some pictures from previous years. You can see me and Tom on the top right. It's just some pictures of the setups, what some of the cars look like, what the track looks like. And I have a video that will very conveniently give you a rundown of how exactly it works.
Flipping switches and off they go.
I think the Chem E competition is one of the best things that we do at AIChE.
Your time starts now.
It's an opportunity to work on a project independently in teams.
How do you know that we'll start connecting them?
I think they have a lot of fun doing it. They have a lot of fun building the cars and testing them and running them. And sometimes cars don't go, sometimes they go backwards. It's all part of the fun.
Well, I think the students all think it's very exciting as to where their car stops.
Have that car start from the line and stop as close to the line as possible. It gives me a lot of satisfaction, a lot of happiness. See, my work is paying off.
So it's cool to be able to build something real and have it in your hands and then see it compete well in competition.
I think the hands-on application lets you pull it all together, take the classroom learning and apply it in real-world situations.
The Chem E Car is that bridge between. It gives you the step up from the labs experiments. We're really putting all of our knowledge to the test.
So you have to develop the reaction, you have to do the...
All right, that pretty much gives you the gist of everything. All right, and now we're going to go into a little more detail on what exactly we did for our car. Tom, take it away.
Yep. Yeah, so these next 3 slides are going to focus on some of the 3 main focal points of our car, which involve the propulsion mechanism, the stopping mechanism, and the mechanical and electrical design. And so in this slide, first I'm going to focus on the propulsion mechanism. So last year our team chose to construct what's known as a zinc air battery to power the car. And before I talk specifically about the zinc air battery, let me just summarize the fundamental components of a battery. So every battery is composed of an anode, a cathode, and an electrolyte. And the anode, which is the negative terminal, is where the electrons flow from. And then the cathode is where the electrons flow to. And the cathode is the positive terminal. Now, the electrolyte is a liquid pathway that allows ions to be transported from the cathode of the battery to the anode in the presence of a barrier that's separating all other materials from passing through. And so batteries create like this special type of chemical reaction, which is known as an electrochemical reaction, where the active materials present in the anode and the cathode are completely separated from each other, using like a filter paper. And that only allows ions to pass through. And so the key here is that these ions that flow through this filter paper contain a negative charge, and then these charges have to be balanced in order for this process to work. And the way to do this is by connecting an external wire from the anode, so the negative terminal of the battery, back to the cathode. And that'll allow negatively charged electrons to balance out the total charge. Because remember, in the cathode, it's losing negative ions, so there's a net positive charge there. And at the anode, it's gaining negative ions, so there's a net negative charge. And that can't happen. We need a net neutral charge. So at the anode, we need to give up some of the electrons and put them back to the cathode. But what we can do is we can build an electric circuit in between the anode and the cathode, and that can do useful work for us, such as powering the motor on the car. Now, the unique part about a zinc air battery, as it differs from many other common types of batteries like lithium ion or alkaline or lead acid batteries, is that the cathode material only contains water and oxygen from the air. And the advantage here is that water and oxygen are in a gas and liquid state, unlike other batteries, which generally contain, a solid base metal at the cathode. And so in order to exploit this non-solid state cathode design, we used a substance called activated carbon, which dramatically increases the available surface area for oxygen and water to react at the cathode. And so the picture shown in the bottom right here displays the activated carbon under a microscope. And you can see all of those like little microscopic pockets that collectively increase the total surface area for the reaction to occur. So adding this activated carbon significantly improved the performance of the battery so that we didn't need to build, like a bunch of cells to get equivalent power output. And this is a big advantage for us at the competition when we're under a time constraint. So if we only have to make 6 or 7 cells as opposed to 11 or 12, that's a big advantage for us. Move on.
Oh. Wait, I'm not sure what's this. Wait, I think.
Yeah,
I think I might.
Yeah, I think it.
By any chance, can you share it? Because I think I accidentally deleted it.
Yeah, I can do that. Sorry. Where were we? Oh, yeah, stopping mechanism here. Okay. Can you see my screen?
Yes.
Cool. All right, so moving on to the stopping mechanism, our team used something called an iodine clock reaction to stop the car. And the iodine clock reaction acts as a chemical clock, which can be adjusted by changing the concentration of the reactants present in the reaction. So the idea is that we start with 2 clear solutions that are mixed with a variety of substances that are present in 2 separate containers, as you can kind of see from this schematic here. Once you mix these solutions together, a chemical reaction starts, but initially it'll seem as though nothing happened. So you won't observe any heat loss, there won't be any bubbles, it'll just look like, like water, like nothing happened. But after some amount of time, the solution will change from clear to dark, and that signals the end of the reaction. And this happens very, very quickly. So understanding why the solution changes color and why there's this time delay requires a little bit of knowledge about the reaction chemistry. But I'm going to try to simplify this as much as possible. So I have each reactant and product assigned to a different letter and color coded according to the chemicals displayed in this upper left corner here. But I excluded chemicals X and Y in the reaction because these are just non-useful byproducts, these X and Y here. So they're not that important really to understand. But this reaction contains 2 separate steps. And this is the important part to understand. So in the first step, chemical A reacts with B to form C and D. To form C and X. And these numbers here just represent the relative amounts of chemicals that is needed for the reaction to take place. So it's like 1 part A to 3 part B to make 2 parts of X and 1 part of C. What happens is that C is created in the first step. However, in the second step, you'll notice that C is being consumed. So C is the product in the first step, but the reactant in the second step. And so the key here is that in the first step of the reaction happens very slowly, while the second step happens almost instantaneously. And what that means is that there's virtually no amount of chemical C present in the container at any given time because of how quickly it's being consumed by the chemical D in the second step. But unlike chemicals A and B in the first step, which are present in abundance, there's only a small quantity of chemical D present in the container. And depending on how long we want the car to travel will determine how much of chemical D that we add. So this means at some point the amount of chemical D will eventually run out and there will be none left. And when this happens, the second step of the reaction no longer takes place. And the immediate result is an accumulation of chemical C in the container. When this happens, when chemical C starts to accumulate in the container, that's what creates this dark bluish black solution that you see here in the bottom right. So how can this reaction be used to our advantage? Since our car uses an electrical circuit, we can add electrical components to this circuit that changes the way the circuit behaves. And one of these components that we can add is a resistor, which changes the flow of electricity based on the resistance value. And this is kind of like a valve in a pipe flowing with water. How the valve can vary the flow depending on how much is open. So the type of resistor that we use in the circuit is called a light-dependent resistor, which changes resistance based on the amount of light hitting the surface of the resistor. In the schematic shown here, we're placing an LED on one side of a beaker, and then we are placing a photoresistor on the other side. And because the solutions are initially clear, there's enough light hitting the surface of the photoresistor to allow sufficient electrical flow through the circuit. But once the solution changes from clear to dark, the light can no longer reach the surface of the photoresistor, and that results in a spike of resistance in the circuit, which ultimately cuts off the supply of power to the motor and stops the car. So that's how the stopping mechanism there works. And then the last part here is the mechanical and electrical design of the car. And for the electrical design, there are 3 loops in this circuit. and they're each labeled with different colors. A loop is basically just a closed path that allows electricity to flow. And starting from this left loop here, this magenta color loop, you'll notice that this is the loop that contains the LED that I was talking about earlier. And this one's very simple. It doesn't contain any other components other than the LED and then a 3-volt onboard battery. And so once the switch on this loop is turned on, the LED will just turn on. In the middle blue loop here, you'll notice that this is the loop that contains the photoresistor right here. And as I mentioned, the LED will shine through the container and it'll reach the photoresistor on the other side. So in this loop, the connection travels through what's known as a relay switch here. This little black box is a relay switch. The relay switch is a device that contains an internal magnetic coil and a switch that turns on or off based on the magnetic force from the coil. So when resistance values are low in the circuit, there's enough of this magnetic force to keep the switch open. But when resistance suddenly increases because the light can no longer hit the photoresistor, that's when the switch will close. So then that leads us into the last loop shown here in red. This loop contains both the zinc air battery and the motor which drives the car. And then depending on if this internal switch is on or off is going to determine whether the motor will operate. So that's really how this electrical circuit works and connects together. And then on the right here, you can see a couple pictures of our car in more detail here. We used this dual axle DC motor here, which is geared to a specific gear ratio, which moves our car at a relatively constant speed. And this is a really simple design. It's basically just we have this acrylic platform which we use the laser cutter to make precision cuts and where to place these holes on the car so that the motor's aligned perfectly straight. And yeah, that's a little bit more about our car here. We use this breadboard circuit which interconnects all of the different connections together, and it just makes the design overall a lot easier so you don't have a bunch of wires everywhere. So and yeah, that's about it. So if there's any questions, we'd be happy to take them. Otherwise, thank you guys for joining us.